Section 6.2, Taylor series, of the properties of Taylor series, specifically the formula that's used to compute the coefficients of a Taylor series. And we'll look at some characteristics of Taylor series and then also utilize Taylor series for three important functions that we run into pretty frequently. If you look back at the notes from the last section, in every example we were provided with a given series representation of a function, and then we were asked to state properties of that series representation or perform some modifications of that series. In this section, and in a lot of contexts, the problem is sort of reversed. We will not be given a series representation of a function, but our task will be instead to construct such a series ourselves. This could be constructed for a certain class of functions using what I call the Taylor coefficient formula. Here's how I think of it. A power series always consists of two components. First, we have what I've called the power terms, or the variable terms, and then secondly, we have the coefficients. The variable terms, or the power terms, are completely predictable. I know that every series, the power terms look exactly like this: x minus x naught to the 0, x minus x naught to the first, x minus x naught to the second, etc. So those terms, that component of the power series, is obvious. On the other hand, coefficients change from series to series. Coefficients are unique to a specific series. So anytime it is our goal to construct or build a series representation of a function, we'll always focus on identifying or computing exactly what the coefficients of that series are. This is a key idea that we'll rely on in the next section when we use series to solve differential equations. In some cases, for a certain class of functions, these coefficients can be computed directly by a formula. Again, I've called this formula the Taylor coefficient formula. And in this definition here, we identify that if f of x is defined at the center value x sub 0, and if infinitely many derivatives of f are also defined at that point x sub 0, then we can construct a Taylor series representation of the function centered at x sub 0, given kind of generically in this form here. Again, I see those two components. I see the power terms, or the variable terms, which are predictable, and then I see the coefficients. And the coefficients in this context can be directly computed using this formula here. So this formula is what I refer to as the Taylor coefficient formula, and it states that the nth coefficient will be the nth derivative of my function evaluated at the center value divided by n factorial. One way that we can use this formula is to use it directly to compute coefficients of a series. Now, I know that the full series representation of a function requires infinitely many terms, so that would require me to directly compute infinitely many coefficients. That's obviously not reasonable, but there are a lot of contexts in which I can use this formula simply to identify the first several coefficients and then build an approximation of the full series representation by building the first several terms of that series. This is demonstrated in example 1, where we're asked to build an approximation of the Taylor series representation of f of x equals natural log of x, centered at 1. So on the one hand, I know exactly what this series looks like. At least I know what the power terms look like. Since this series is centered at 1, I know that the power terms will be x minus 1 to the 0, and then x minus 1 to the first, etc. The question is what coefficients go on those power terms. That's what makes this series representation unique. I've left the sort of room for myself here to fill that in a second, and computing those coefficients is exactly the point of this problem. Here's a reminder up here in orange of that general formula, and it indicates that I need to calculate the derivatives of this function evaluated at this center value, and then divide those derivatives by an appropriate factorial. So let me do this. Let me start by calculating the function along with several of its derivatives. We're actually told here to find the first 5 non-zero terms. So I've set up room to calculate some derivatives. And then once I've evaluated those derivatives in terms of the general derivative, then as the formula requires, I'll plug in the center value into each of the derivatives. The numerical values that I get once I've plugged 1 into each of these derivatives isn't exactly my final coefficient. The last step is I'll need to divide by the appropriate factorial. This is a pretty friendly function in terms of derivatives, so it shouldn't be hard to calculate all of the necessary derivatives. Here I've written out those derivative functions. Next, I will plug the center value into each of those. And then the last step to build the actual coefficient will be to take each of these derivative or function values and then divide by the appropriate factorial. And it is now clear that I got a little ahead of myself writing this function out. So let me erase that to create a little bit more space. And I also noticed that my very first coefficient, a sub 0, is 0. Since we were technically asked to find the first 5 non-zero terms, I'll need to add sort of one more row to these computations. And now let me just simply simplify these coefficient values a little bit. Obviously I can evaluate these factorials and then do some reducing in these fractions. So here I've written those final coefficients in pink, and now I will just insert those coefficients onto the appropriate power terms, and I'll get an approximation of my Taylor series. So this is what would sometimes be called the 5th degree Taylor polynomial, because it goes up to an x to the 5th power term. And again, I have simply inserted the coefficients that we just calculated onto the necessary power terms. And so this will give me a moderately good approximation of my original function f of x, as long as I choose x values near this center value of 1. And here I've graphed the original function, natural log of x. That's this kind of thick black line. And then I've graphed each of the individual Taylor polynomials. The first degree Taylor polynomial would just be the function x minus 1. And you can see that in kind of this reddish color here. The second degree would be that x minus 1 term in addition to this negative 1/2 x minus 2 squared. That gives me this parabola that's kind of an orangish. And as we're accustomed to seeing, as the number of terms increases, this series representation becomes a better and better approximation of the original function, centered at, in this case, the x value 1 here. And as I said, this is practical if we just want a few number of terms to build an approximation of our original function. If I wanted to calculate 50 or 60 or 100 terms, doing this computation by hand would be sort of tedious. Actually, in this particular case, there's a pretty clear pattern to what these coefficients end up being. You may have noticed as I wrote this out that the signs appear to be alternating, positive and negative. And then I essentially get this unit fraction 1 over some value, and this value ends up corresponding exactly with the power. So I expect the next term would be negative 1/6, x minus 1 to the 6th. After that, I'd have positive 1/7, x minus 1 to the 7th, etc. So in this particular case, there appears to be a pattern to these derivative values, which then leads there to be a clear pattern in terms of the coefficients. This, of course, happens with other functions as well. There's other well-known functions for which there's a very clear pattern to the derivatives. Think of e to the x. All of its derivatives are e to the x. Therefore, in the case of some functions, when a very clear pattern exists for the derivatives of those functions, we can actually come up with explicit expressions for all of the coefficients. Doing so in the case of these three functions yields these well-known series representations. These are Taylor series that are centered at x equals 0. You may have heard these referred to as Maclaurin series. That's just a special name for any Taylor series that's centered at 0. And these three functions you of course recognize as being very, very important functions. And so these three series representations are so ubiquitous that we essentially need to have these memorized. So then what I'd like to demonstrate in our final example is how a known series, such as one of these three here, can be used, modified in such a way that we can perform operations with functions in terms of their series representation that we couldn't necessarily perform in terms of the original form or the original statement of the function. Let me show you what I mean. Here in example 2, we're asked to first find a series representation of cos of x cubed centered at x equals 0. And then once we've got that series representation, we're asked to identify an antiderivative of this function. If you think about it, this function can't be integrated analytically. We can't directly identify an integral of this function. U substitution won't work, integration by parts won't work, none of our integration techniques will work. And yet, in this problem, we'll be able to find an antiderivative in terms of the series representation. Let's start by writing a series representation of our original function f. I've provided a little reminder of the series representation for cosine of x. And now I simply want to take these x values and instead of just writing x, I'll substitute in x cubed. And then if I want to, I can do a little bit of simplification here, simply distribute that exponent through. And then let me just remind myself that we've called this function little f of x. And now, as we demonstrated in the previous section, series representations can be differentiated, and therefore they can be anti-differentiated. So I can simply anti-differentiate this series representation of our function. I've called that antiderivative capital F, and my original function is simply x to a power. So in order to anti-differentiate that, I have added 1 to the power, and then I've divided by that new exponent, the new power on x. Note that I've also included a constant of integration, because when I anti-differentiate, I know that there could be that constant there. So this is an antiderivative of the function cos of x cubed, and I admit it feels a little strange to write it in this series form, but as I tried to reiterate in the last section, I can get good approximations for the antiderivative by simply looking at a few specific terms of this series. And in a lot of contexts, such an approximation is really all I need. So utilizing the series representation of this function, we've been able to perform an operation, specifically anti-differentiation, that we could not perform on the original form or the original version of our function. Those are all of the properties that I wanted to reiterate about Taylor series in this section. We're ready now to move on to 6.3 and look at how series can be used to solve differential equations.